Welcome to a video on solving quadratic equations using the completing the square method. So to get started, I wanted to think about polynomials and recognizing them as perfect squares. So these pictures may not be familiar to you, but the one on the left, to explain it, this blue square has a dimension of x by x, and that's where it gets its interior name x squared. That's because x times x is x squared. These little squares at the bottom right are just unit tiles. They have a dimension of 1 by 1. So this is a length of 1 here. This is a length of 1 here. And then 1 times 1 is 1. That's where it gets its interior area name of 1. The other tiles that are green have dimensions of both 1 on one side, and as you can see, it's x on the other side. And then 1 times x is x, and that's where it gets its name. Now, I want to relate this to a polynomial. As you can see, this picture that I have here has a dimension of x plus 1, or x plus 2 end to end this way. And likewise, down the side, it has a length of x plus 1. So the full length here is x plus 2 as well. And so I want to look at the polynomial x plus 2 times x plus 2, or known as x plus 2 squared. Well, let's see what happens when we multiply that out. So we have x times x, that's x squared. X times 2, keep that in your head, that's 2x. And here's why. Plus another 2x, that's a grand total of 4x. And then lastly, 2 times 2 is 4. What I'd like you to notice is that this solution matches the interior of this picture. Right? The x squared is the big blue square. The 4x is a combination of these two at the bottom, 1, 2, 3, 4 x's. There's a total of 4 x's. And then the 4 in the bottom corner is the units, 1, 2, 3, 4. On the right-hand side, we have an incomplete square. An incomplete square has a blank spot at the bottom right, makes it not a square. So the question is, how many tiles would it take in here to kind of fill this out? And you could probably just use your imagination and go, oh, okay, well, if we extended these lines down like this, and we extended these lines over, you can see how many tiles it would require. But on paper, it would look different. We would start with our term x squared, and then counting the x's on the bottom and the right-hand side, we have 1, 2, 3, 1, 2, 3, 4, 5, 6 x's, right? Plus something. I'm going to leave a little blank, but we want this to be a perfect square. Right? And that's what the goal is, to complete a square. So the thing to notice is that this length has a length of x here, but these all have 1s. So it actually ends up being x plus 3. And the length left to right, since it's a square, is the same as x plus 3. And you might notice that there's a relationship between the number of x's and the length of the side. In this case, the length of the side is x plus 3, 3 being half of 6. So then the next question is, well, how many tiles, right? How many tiles do we need in the bottom right? And you can see here in the bottom right hand, it looks to be 9 tiles. And the reason is because it's 3 this way, right? 3 this way, and 3 this way as well. And 3 times 3 is 9. So that value will go here. In general, we want to think of what's the relationship between the number of x's, the unit, and the factored form. So let's take a look at a few examples of that without pictures. These are just polynomial expressions. So if I had x squared plus 10x, and I was wanting to complete the square, right? I was wanting to write it as a perfect square, like that's what I want to do. What I would first think of is, okay, this could be x plus something. The way to get 10x is I need a grand total of 10 x's to add between these two terms. But since I'm wanting a square, I want them to be the same. So I'll take 10 and I'll divide it in half. That gives me 5. Well, that is equal to x plus 5 squared. But for it to be truly finished, I have to fill in the blank here. What value would go there? That can be found by just thinking about 5 times 5. Oh, okay, that must be 25. So completing the square, the steps are, in general, take this term here, the number of x is the coefficient, 10, divide it into 2 equal pieces to find this value, divide it by 2, we get 5, and then square that, and it gives us 25, the number in the ones place. We can use this to create our own squares and the previous video, solving quadratic equations with the square root method, to overall have a method we call solving quadratics by completing the square. So let's do our first one. We're going to solve the equation x squared plus 10x plus 5 equals negative 13. Now, the issue with this is, and you can remember from the previous example, is that this left-hand side is not a perfect square. We want to make it a perfect square. And so the way we do that is we first get rid of the constant term. We're going to subtract 5 from both sides, and we get x squared plus 10x. And then I'm going to leave a blank space, equals, in this case, negative 13 minus 5, negative 18. Now, the way that I'm going to make this a perfect square is I'm going to add in a value here so that I have a perfect square. But since it's an equation, I have to add the same value to the right-hand side. The way we find that value, as I showed you before, is to take the number of x's, okay? And we're going to call that, in general, we'll call that b, the b value of a quadratic. And the formula for it is take the b and divide it in 2. You saw that from the picture above, and square it. In this case, we have 10. Dividing it by 2 gives us 5, and squaring it gives us 25. That's the number we need to add in to both sides of the equation. So going back to the equation, I'm going to add 25 on the left-hand side. I'm also going to add 25 on the right-hand side. What that causes is it causes me to be able to factor this to x plus 5 times x plus 5, or x plus 5 squared. The right-hand side, I'm just going to evaluate negative 18 plus 25. That's 7. Now you might notice this looks pretty familiar from a previous video. We have a perfect square. We're going to use the square root method from here on. We're going to take the square root of both sides. The square and square root cancel out. I just get x plus 5. Don't forget the plus minus. The square root of 7 is not a nice whole number, so I'm going to leave that as square root 7. And the last step is to subtract 5 from both sides. All right, x would be equal to negative 5 plus or minus the square root of 7. Yes, you can write that also as negative 5 plus the square root of 7 and negative 5 minus the square root of 7. For a lot of you STEM majors, maybe engineering majors, physics majors, whatever, you might want those numbers to be usable, more usable by evaluating those as decimals. In this case, I'm going to leave it as an exact answer. So there's the overall method. You're going to take your equation, find a way to turn it into a perfect square so that you can then use this square root technique. All right, we'll need to see another example of this. So let's take a look at a second example. I'm going to solve with the same technique, x squared plus 7x plus 2 equals 0. So what you immediately want to do is get rid of the constant term because it's going to get in the way of making a perfect square. X squared plus 7x equals negative 2. Now, what we need to do is we need to add in some value to both sides to create a perfect square. So that technique was to take the b term, in this case 7, divide it by 2, and square it. If you wanted to work this in fractions, you certainly could. You could just square that and get 49 over 4. Or if you want to do it in decimal, you can do 7 divided by 2 is 3.5, and then you square that, and you should get, and this is an exact answer, 12.25 as a decimal. I'm going to use that for this particular problem. So I'm going to write in, I'm going to add 12.25 to both sides. I'm going to contrast that with fractions in just a second so you can see the difference. Okay, so when I factor it, it looks a little tricky now. Like, oh, where does this 12.25 come from? And how does it relate to the 7? And that issue is because we didn't ever rewrite this as a decimal, right? I said it out loud, but I didn't rewrite it. That's 3.5 squared. So it turns out that 3.5 is exactly half of 7. So every time we write our perfect square, when we write this, we're going to be careful of the sign. This is plus. It's going to be half of the b value, 3.5 being half of 7 squared. On the right-hand side, I have 12.25 and negative 2, putting those together. So that would be 10.25. All right, now I have a perfect square. I can employ the square root method. Square root to the left, square root to the right. X plus 3.5 is equal to plus or minus the square root of 10.25. That's also not a nice number, so I'll just kind of leave it for now. Subtracting 3.5 from each side is my last step. So x is equal to negative 3.5 plus or minus the square root of 10.25. Now, I told you I was going to contrast that with a fraction to close out this video. If instead of adding 12.25, you had added a fraction, you would find that the answer looks a little bit more clean and we have a lot of integers rather than decimals in our answer. So I'm going to pick that up from there. So if we would go back and revisit that, x squared plus 7x plus something equals -2 plus something. The other way to go about this is to take the b, 7, divided by 2, and square it. And when it doesn't go in evenly, just square the whole number. 7 times 7 is 49, 2 times 2 is 4. And you would instead add 49/4 to both sides of this equation. And so the advantage is, you'll see it in just a second. When I write it as a factored form, I'm just going to write 7/2 rather than the 3.5 that I wrote before. On the right-hand side, I do have a little bit of computation, -2 plus 49/4. I know that -2 is equal to -2 over 1. If I multiply that by 4 over 4, I get -8/4. And so this expression really is -8/4 plus 49/4. So let's do one additional step before our square root. We're going to simplify the right-hand side. -8 plus 49 is 41/4. Now we use the square root, and we get just x plus 7/2. We'll get plus or minus. I can't really do the square root of 41 as a whole number, so I'll leave that as square root of 41, but I can evaluate the square root of 4. That's just 2. And my last step is to subtract 7/2 from both sides. And I get x equals -7/2 plus or minus the square root of 41 over 2. And you could write that as 2 terms with curly brackets, as I've shown before, but you can see that that's like the other answer, just in fractional form. Well, I hope this helps you learn a little bit more about how to use the completing the square technique.